Think about this for a second. Which elements can bleach your clothes, disinfect your drinking water, protect your teeth, but at the exact same time cause absolutely severe chemical burns? It's an incredible paradox, isn't it? We interact with this highly reactive, honestly quite dangerous family of elements every single day, relying on them for our fundamental health and global sanitation.
Welcome to today's Explainer. I'm your host, and today we are unlocking the secrets of the most extreme column on the periodic table. We're talking about Group 7, the halogens. Let's dive right in and break down their incredible properties, their reactivity, and exactly how they behave when you get them into the lab.
Here's how we're going to break it down today. First, we'll meet the halogens, then dive into their reactivity and oxidizing power. Check out the halides as reducing agents. Look at some displacement reactions. And finally, wrap up with identification and disproportionation.
All right, Part 1. Meet the halogens. Let's look at how their physical properties shift as you move down the group.
So you've got your main four players: fluorine, chlorine, bromine, and iodine. You probably know they all hang out as diatomic molecules, traveling in pairs like F2 and Cl2. But what's really wild is how drastically they change just sitting at room temperature. We go all the way from fluorine, which is this pale yellow gas, down to iodine, a chunky gray-black solid. And as you travel down that group, the boiling point skyrockets. Why is that? Well, it's all about size. Bigger molecules mean way more electrons, which creates much stronger van der Waals forces. It's basically like a magnetic stickiness. You're just going to need a lot more heat energy to pull them apart.
Moving on to Part 2, reactivity and oxidizing power. Let's talk about the atomic tug-of-war.
So, halogens make their living by stealing an electron to form a halide ion. That makes them oxidizing agents. But here's the kicker. Their reactivity actually drops off as you go down the group. Fluorine is a completely ruthless electron thief, while iodine is honestly pretty mild. The reason? Electron shielding. As you drop down the group, you're packing on more and more electron shells. This builds a literal shield between the positive nucleus and the outer edge. The atom gets bulkier, the atomic radius increases, and that incoming electron is physically just kept further away. It's simple. The larger the atom, the weaker its pull on that extra electron.
Which brings us to Part 3, halides as reducing agents. This is where we get a massive plot twist.
If the halogens are these aggressive electron thieves, their alter egos, the negatively charged halide ions, are basically the complete opposite. They are super generous reducing agents. And unlike their halogen counterparts, their reducing power actually increases as you go down the group. It makes perfect sense if you think about it. Those larger halide ions, like iodide, have tons of shielding and a huge radius. They're holding onto their outer electrons so loosely that they're more than happy to just give them away.
Let's see what this looks like in the lab. When you mix solid sodium halides with concentrated sulfuric acid, things get pretty dramatic. Sodium fluoride and chloride, they don't reduce the acid at all. You just get some hydrogen halide gas. But sodium bromide, that one's got enough kick to partially reduce the acid, giving off this intense orange bromine vapor. And then there's sodium iodide. It is such a beast of a reducing agent that it forces the sulfuric acid all the way down to hydrogen sulfide. You'll know it immediately because of the brutal rotten egg smell. Plus, you get solid sulfur and this really gorgeous purple iodine vapor.
All right, Part 4, displacement reactions. Welcome to the halogen competition.
The rule here is cut and dry. A more reactive halogen will absolutely bully a less reactive one and displace it from its salt solution. A stronger oxidizing agent is going to oxidize the weaker one's halide ion. We usually use a cyclohexane layer test to spot the winners and losers here. Drop some chlorine into a bromide solution. The chlorine boots the bromine out, and your liquid layer turns orange. Add chlorine or bromide to iodide, and boom, you get a deep violet or purple layer as iodine is formed. But watch what happens if you add bromine to chloride. Absolutely nothing. Bromine just doesn't have the muscle to kick chlorine out of its spot.
And finally, Part 5. Identification and disproportionation. Let's look at laboratory tests and atomic paradoxes.
Let's start with a classic setup involving sodium hydroxide. The absolute most important thing to remember here is that temperature dictates literally everything. If you react chlorine with cold, dilute sodium hydroxide, you end up with sodium chloride and sodium chlorate I, which, by the way, is just everyday household bleach. But switch that up and use hot, concentrated sodium hydroxide, you get a totally different product, sodium chlorate 5. The oxidation states completely change. So whenever you're dealing with this reaction, you have got to specify the temperature.
Now, in both of those reactions, chlorine is doing something super interesting called disproportionation. This is a fancy way of saying a single element is being oxidized and reduced simultaneously in the exact same reaction. The best everyday example of this is just adding chlorine to water. Chlorine starts out at an oxidation state of 0. Then it splits paths. It forms HCl where it's reduced and hypochlorous acid where it's oxidized, one element going in two completely opposite directions at the same time. And, fun fact, it's that hypochlorous acid that actually gives chlorinated water its ability to disinfect.
Okay, so how do you definitively identify these halides when you're standing at the lab bench? You use the silver nitrate test. The order of operations here is absolutely critical. Step 1, and this is the one everybody forgets, you have to add dilute nitric acid first. This wipes out any pesky carbonate or hydroxide ions that would totally give you a false positive. Only after that's done do you move to step 2 and add your silver nitrate solution. Then, step 3, you add ammonia just to confirm the solubility of the precipitate you just made.
So what exactly are you looking for? Well, chloride gives you a white precipitate, bromide gives you a cream one, and iodide gives you yellow. Now, under dim lab lights, white and cream look practically identical, which is exactly why that ammonia step is your ultimate safety check. Silver chloride dissolves super easily in just dilute ammonia. Silver bromide is a bit more stubborn. You're going to need concentrated ammonia to dissolve that. And silver iodide, completely insoluble, won't budge. This drop in solubility is a perfect visual representation of how the bonds become increasingly covalent as you drop down to that larger, highly polarizable iodide ion.
Now, I know it's easy to get totally lost in the equations, but we have to ground this theory in the real world. These aren't just letters in a textbook. Chlorine is literally out there right now, disinfecting the tap water you drink and the pools you swim in. Fluorine is sitting in your bathroom, added to your toothpaste to convert your tooth enamel into much tougher fluoropathite. Iodine is a crucial trace element your body absolutely needs to regulate thyroid hormones. And bromine is hard at work in flame retardants, keeping our homes safe.
Which leaves us with this final, honestly profound question. How does some of the most toxic, aggressive elements on the entire periodic table end up being so absolutely essential for human health and global sanitation? It is the ultimate chemical paradox. They have enough destructive power to cause severe chemical burns, yet they are protective enough to ensure the water we drink won't make us sick. Thank you so much for joining me for this explainer on the incredible dual-natured world of the halogens. Keep questioning the chemistry around you, and we'll see you next time.